Okay, this is lesson 13, applications of modeling with linear equations. We're going to solve applied problems. We're going to solve geometry problems, motion problems, mixture problems, modeling with linear equations. First thing you want to do is read the problem until you understand it. You want to assign variables that represent unknown values. They don't have to be X and Y. You can like R. You can assign R for rate and T for time and so on. But technically, you can assign any variable you want. But you want to try to assign variables that you can remember and work with. Okay, you want to write the equation, and this right here, step 3, is the most critical part because you have to remember certain equations, like distance equation is equal to rate times time, or the area of a circle, pi r squared. So on this step 3, you're going to have to rely on remembering certain equations for certain circumstances, and then solve and state your answer. Now your answer, you're going to get x equals to some value, but that may not necessarily be your answer. You may have to go back and add it into some numbers to get, like for dimensions in a rectangle, like one side is 3 more than the other. Well, if you find x equals to 5, well, that's only one side. That might just be your width. You may have to go back and add 3 to 5 and get 8 for the other side. So you may have to go further than just find x and then check your answer. All right, finding the dimensions of a square. We're going to take this and we're going to work with the problem from here. Okay, here it says find the length of each side of a square. Now it helps to draw a picture. So here's our square. Length of each side of the square is increased by 3 centimeters. So we have, here's a side and it has x, but we're saying that each side is increased by 3. So this would be x plus 3. So since it's a square, all the sides are the same. So they're all going to be x plus 3. The perimeter of the new square is 40 centimeters more than twice the length of the original square. Well, twice the length of the original, well, what was the length of the original square? We don't know. So it's x. So here we're saying twice the length of the original square, so that would 40 centimeters more than twice the length of the original square. Well, let's look at the multiplication part first. Twice the length of the original square. What's that? Well, since the length is x, that would be 2x, right? But we're saying 40 more than 2x. So it would be 2x plus 40. Okay, now this is where we get into the equation part. We know that the perimeter of the square is equal to the sum of each side, right? So we're talking about if each side is x plus 3, we can put x plus 3 4 times, or we can say x plus 3 times what? 4. And since the equation for the perimeter of the square is 2x plus 40, we would substitute 2x plus 40 in for p. So that would be 2x plus 40 equals to 4 times x plus 3. All right, questions up to this point? Okay, so Travis, what would we do here? Yeah, distribute the 4, right? So that would be 2x plus 40 equals to 4x plus 12, right? And then solve for x. So we would apply minus 2x, and we get 40 equals to 2x plus 12. And then apply minus 12 to each side. We get 2x equals to 28. And then we divide by 2. And we get x equals to 14. Well, what does that represent? Find the dimensions of the original square. Okay? So we would say here we're looking at x equals to 14. But we want the perimeter of the new square. We want to find the dimensions of the original square. So we have to take that and we have to say, all right, each side of the original square measures 14 centimeters. So this would be 14 centimeters. Okay? Questions with that so far? Okay, well, what would be the length of, so let's go back to our problem. And we did all this. So this is what we got right here, 14 centimeters. Step 6, go back to the original problem to see any conditions are satisfied. The length of the side of the new square would be 14 plus 3 is 17. So when we substitute 14 back in to our equation over here, everything checks. We get 68 equals to 68 on both sides. Okay, next. In a motion problem, the components of distance, rate, and time are denoted by the letters D, R, and T, usually. That's basically what we use for distance, rate, and time. So distance equals to rate times time. So if we were to divide T to both sides, we could get rate equals to distance over time. Or if we divided R to both sides, we would get time equals to distance over the rate. All right, so here we have a problem. Maria and Eduardo are traveling in a business conference. The trip takes 2 hours for Maria and 2.5 hours for Eduardo, since he lives 40 miles further away. Eduardo travels 5 miles per hour faster than Maria. Find their average rates. Oops. So here we see that Maria, first we have to find Maria and Eduardo's average rates. Okay? And then we're going to put them into this table here. So let's do that. It's easier if I do it this way. Minimize it. All right, so to start with, we want to come up with a table where we have rate time and distance. And we have Maria. And we also have Eduardo. Okay, now we said that the trip takes 2 hours for Maria. So where would the 2 hours for Maria go? Would it go into rate, time, or distance? Sydney? Time. Yeah, we go into time for Maria, right, which would be 2. And Eduardo, well, what would we put there? 2. Right, 2.5. Okay, since he lives 40 miles away, Eduardo travels 5 miles per hour faster than Maria. Well, we don't know what Maria's rate is, so we're going to say R. Maria is traveling at rate R. That means since Eduardo is traveling 5 miles per hour faster, okay, than Travis, what would Eduardo be traveling? Right, R plus 5. And since distance equals to rate times time, that's what we're going to put here for the distance part. This would be 2. Maria's distance would be 2R. And Eduardo's, what would that be? Dylan? Well, Dylan, look over here. If distance equals to rate times time, right? And Eduardo's, what's Eduardo's rate? R plus 5, and his time is 2.5. Then what would we put here for distance? Yeah, so that would be, or you could put 2.5, but you got to put it in parentheses, right? Because that's 2.5 times the whole expression. Okay, so that would end up being now from here we know that they're traveling the same distance. So this would be the distance for Maria, and we'll call it D sub M, and this would be the distance for Eduardo, D sub E. So we're saying here that we know that the distance for Maria and distance for Eduardo are not the same. We do know that Eduardo lives 40 miles further away. So in order to get both sides to balance, what helps is to write DE equals to the distance for Eduardo equals to the distance for Maria. Eduardo lives 40 miles further. So to get both sides to equal, where would we have to add the 40? To the Eduardo side or the Maria side? Well, for Eduardo's, let's say Maria's 20 miles away, and Eduardo's 40 miles away. Well, let's say he's 60 miles away. So that means that in order for both distances to be equal, we'd have to add the 40. See, Maria is 20 miles away, and Eduardo is 60 miles away. Let me use black. See if that works better. Let's say Maria is 20 miles away, and Eduardo is 60 miles away. So in order for both sides to equal, right, we would have to add the 40 to which side? Maria's or Eduardo's side? Maria's. So, but we don't know what the distance is. We know that Eduardo is 40 miles further, so we would have to add the 40 to Maria's side. Okay? Well, we know that the distance from Maria is 2 times the rate, but we have to add the 40 to that. And then Eduardo's, that's 2.5 times r plus 5. Okay, so that's going to give us 2r plus 40 equals to 2.5 r plus, this is going to be 12.5. Okay, now at this point we can solve for r. So we can apply minus 2r. So this would be like 2.0r, right? And so we get 40 equals to 0.5 r equals to 12.5 and minus 12.5. So we have to add another 0 here. And so that would be 3, 9, and 10. So that would be 5.7, 27.5 equals to 0.5 r. And so we can divide by 0.5. Okay, and we get r equals to 55. All right, so if r equals to 55, then find their average rates. Well, r equals 55. R is whose rate? Maria's or Eduardo's? Maria's, right? So this is Maria. And what about Eduardo? What do we got to do there? That would be 55, right? But what? If Maria's is 55, Eduardo's has to be, Maria's is r and Eduardo's is r plus 5. We found Maria's is 55 miles per hour. Then what do we have to do with Eduardo's? Add 5, right. And so we get Eduardo is 60 miles per hour. Maria's is 55. Okay? Questions with that? All right. Does it help to have this here as we're doing the problems, or does it matter? Yeah? Okay. All right. And so that's what we did here. It shows the same thing as what we did on the PowerPoint notes. And from there, you can check it. Go back to this equation, put 55 into both sides, and both sides should equal. Okay? All right, in a mixture problem involving solutions, the rate percent of a concentration is multiplied by the quantity to get the amount of pure substance. So we're looking at a percentage times, usually it's in liters. Okay? And the final mixture is the concentration of the two solutions. So you want to think of it in terms of, like, one of them, you got one solution in one container, you got another solution in another container, and you mix the two. You pour the two into a third container, and then you're going to get a different percentage. You're going to get a different strength of the solution. All right, so from there, okay, here we have Lisa is a chemist. She needs a 20% solution of alcohol. She has 15% solution on hand. as well as 30% solution. How many liters of the 15% solution should she add to 3 liters of the 30% solution to obtain her 20% solution? Okay. All right, so it helps. Again, we're going to make a table. And so from here, we've got strength, and so for our strength, we've got 15%, and we've got 30%, and we want to end up with 20%. And liters. All right. She needs 20%, so that's what we're going to end up with. She has 15% solution on hand, but we don't know how much of the 15%. But she does have 30 of the 30%. How many she has a 30% solution? How many liters of the 15%? We don't know that, so we would put X. Should be added to 3 liters. So that's going to go with the 30% to obtain 20% solution. So if we take 15%, okay, we have 15%, and we don't know of X. And here's 1 beaker, okay? And we're going to add it to 30% of 3 liters. Okay, so we're going to take those two and we're going to pour them, and we want to make a 20% solution, and so that's going to be X plus 3 in liters. Okay? So that means if we took X amount of 15% and 3 liters of the 30%, how much quantity are we going to have at 20% when we add the two together? Well, we would, let's say this was 2 liters and this was 3 liters. That would make how much here when we poured the two together? 5, right? But we don't know what X is. We do know the other one's 30, or 3 liters for 30. So this would be what? We're adding the two to get X plus 3. Good. Okay, now, and in here, we have to use a decimal. 0.15, 0.3, 0.2. So this would be, now here, this is liters of pure alcohol. And I'm just going to put liters of pure solution. And so it could be anything. It could be alcohol or acid or whatever. Okay, so basically what we're doing is we're just multiplying the two. So this is just nothing more than percent times liters. Okay, so this is 0.15 X. And so this is, what's this next one going to be? 0.3 times what? 3, right. And how about the next one? 0.2 times what? Yeah, X plus 3, but it has to be in parentheses, right? So we're taking these two and we're adding to make this third one. Okay, so this is going to be 0.15x, plus 0.3 times 3 equals 0.2 times x plus 3. Okay? Questions with that? So that'll be 0.15 plus 0.9 equals to 0.2x plus 0.6. This should be 0.15x here. Okay, now if you wanted to, you could, since this is 0.15, you'd have to multiply everything times 100, or you could just leave it as a decimal. So we'll just go ahead and leave it as a decimal. And so now we're going to, since this is like saying 0.20, and this is like 0.15, so we're going to apply minus 0.15 x minus 0.15 x to both sides. Okay, so we're going to end up with 0.9 equals to 0.05x plus 0.6, and then apply minus 0.6, and we get 0.3 equals to 0.05x divided by 0.05. And so we end up with x equals to 6. Okay? But we want how many liters of the 15% solution should be added to 3 liters of the 30% solution to obtain your 20% solution. Okay, so the x represents what? Harley?
6.
Yeah, x is 6, but look back up at the table. Liters for 50%. So did we get what we wanted? How many liters of the 15% solution? So basically this represents liters for 15% solution. Okay? All right. Questions with that? So actually 6, in this case, 6 is our answer. All right? Okay, and so if you wanted to go back and look at the PowerPoint notes, it all shows pretty much the same thing. And then here you just substitute 6 back into our equation, and both sides should get 1.8. Okay, mathematical model is an equation or inequality that describes a relationship for two quantities. Linear model is basically, we know a linear equation makes a straight line, right? Okay, here we have, let me make this bigger. If a vented range hood removes contaminants such as carbon monoxide and nitrogen dioxide from the air at a rate of F liters of air per second, then the percent P of contaminants that are also removed from the surrounding air can be modeled by the linear equation. P for the contaminants equals to 1.06 F in liters plus 7.18, where we want to be between 10 and 75 liters. What flow F must a range hood have to remove 50% of the contaminants? Okay, so in this case, make this a little bigger. All right, so we have, if a vented range hood removes contaminants, we have F liters per second and the percent of P contaminants. All right, so we have our equation right here. We have 50% for P. And we have our equation P equals to 1.06 F plus 7.18. All right, so from here, we're going to go ahead and substitute in the 50. Okay? Well, I kind of gave it away, didn't I? 50 should go in where the P is. So part of this is recognizing where to put what what they give you, the given. So we're going to put 50 equals to 1.06 F plus 7.18. Okay, so go ahead and solve for F. All right, go ahead and do that. Okay, so what do we end up with? F equals what? Travis? 40.39. Okay, 40, yeah, 0.39, 62, and it goes on, right. So they went ahead and just rounded it off to just 40. Okay? All right. So therefore, from here, therefore we remove 50% of the contaminants. The flow rate must be approximately 40.4 liters air per second. All right. Okay. Questions with that? All right, here we have the projected per capita healthcare expenditures in the United States, where Y is in dollars and X is years after 2000, are given by the linear equation. Y equals to 343X plus 4,512. What were the per capita healthcare expenditures in the year 2010? Now keep in mind that what are we starting with here? What would be like our time 0? Let's look at this again. The projected healthcare per capita expenditures in the United States, where Y is in dollars, X is in years, after 2000, okay, are given by this equation. So what were the per capita healthcare expenditures in the year 2010? So we can say that Y is in dollars and X is in years. So if 2000, if it starts so then T0 would have to be 0. So in 2010, this would be 10 years. That would have to be what? We're not going to put 2010 into this equation. 343x, y equals 343x plus 4512. If y is in dollars, x is in years, what are we going to put? We want to know how much in expenditures is going to be in the year 2010. Okay, so what do we do? (2010) is the year, but is that the number of years? It's not, right? Because we're starting at 2000. So that means if time 0 is at 2000, 2010 must be how many years that we're going to use? 10. Okay? And so where does that go in our equation? It goes into X. All right, so go ahead and find the rest of that. And as you're doing that, I'll work this out here. Okay, and so that leaves us with what? Y equals, Travis?
7,942.
Right. 7,942, and that's what? Expenditures, right? Okay, that's part A. Now part B, if this model continues to describe healthcare expenditures, when will the per capita expenditures reach 92,000 or 9,200? Okay, now where does that 9,200 go? Into the Y, right, because that's an expenditure. So this would be 92,000. So this is part B. 92,000, or 9,200 rather, equals to 343x plus 4512. Okay, so solve for x. Okay, and we get x equals what? Sydney?
2013.
Very good. Yeah, because x is going to equal 13.7, but that means we get in year 13, we get 9,200. So we can't go over that because if we go over that, then that's more than 9,200. So we take that, 2,000 plus 13, and so that would give us the year 2013. All right, good. That one was a little bit trickier because they don't want you got to go back and figure out the year, but you don't want to go over that. So our answer here is the year 2013. Okay? Questions with that? Okay. We're going to go ahead and take a break. We'll come back and we'll do the next lesson.